Now today we will discuss about electromagnetic induction, or in short we are calling as EMI. So the phenomena of EMI has been discovered by the Michael Faraday, and with the help of Henry he has performed number of experiments. From that he concluded certain points. So we can say phenomena of EMI has been discovered by Michael Faraday, and with the help of Henry, he has performed number of experiments. So we will discuss first those experiments. With the help of those experiments, we can analyze what is exactly this phenomena. See, the experiment number 1. In this experiment, he took a coil which is connected with a galvanometer. This is a coil, and this coil is connected to the galvanometer. And then what he did, he projected, or we can say this is your bar magnet, suppose. What he did, he took a bar magnet, and that bar magnet is moving either towards the coil or away from the coil. So what he has seen, there is a deflection in the galvanometer. So one thing he did is, suppose if the magnet is coming towards the coil, then he has seen deflection in one side. But when the magnet is going away from the coil, then also he has found deflection in the galvanometer, but in opposite direction. Similarly, if he has changed the polarity of the magnet, it means right now here north pole is coming as well as moving away from the coil. In place of that, suppose here south pole and this is the north pole of magnet. Then also he has found the same effect or same deflection in the galvanometer, but in opposite direction. Rather moving the magnet, if he took the magnet at rest and if the coil is also moving. Suppose coil is moving either towards the magnet or away from the magnet, then also he has performed or he has found the same type of phenomena. So from that he has concluded that when there is a relative motion between the coil and the magnet, then the galvanometer shows certain deflection. So from this we can write, from the experiment 1, what he has concluded. From this experiment, Faraday has concluded when there is relative motion between magnet and coil, then galvanometer shows deflection. It doesn't matter who is moving. And if they are approaching each other, it means if they are coming close to each other, then deflection in the galvanometer in one direction, deflection in the galvanometer in one direction, and when they are moving away, from each other, then the deflection in galvanometer, in opposite direction. So this is the conclusion from this experiment he has found. It means this is your coil which is connected with the galvanometer, and this is a bar magnet. Whenever there is a relative motion between the bar magnet or coil, either they are coming close to each other or they are moving away from each other, then always the galvanometer shows deflection. And if they are approaching, then the deflection in one direction, and if they are moving away, then the deflection in the opposite direction. This is the conclusion from the experiment number 1. Now see another experiment. Experiment number 2. Now see experiment number 2. In experiment 2, he has replaced current carrying coil with a magnet. It means like this. This is a coil in which a galvanometer is connected, and in place of a magnet, he took a current carrying coil like this. If let current is your I in this direction. Now, then what he has found? Same phenomena. It means when the current carrying coil and the coil through which galvanometer is connected, in this case also, whenever there is a relative motion between the coil with the current and coil with the galvanometer, then also galvanometer shows deflection. So from this experiment can be said, even after replacing bar magnet with current carrying coil, then also same type of phenomena has been observed. Same type of phenomena has been observed. It means if there is relative motion, if there is a relative motion between current carrying coil, if there is relative motion between current carrying coil and the coil through which galvanometer is connected, and the coil through which galvanometer is connected, then galvanometer shows deflection. Then galvanometer shows deflection in the same way as when it was bar magnet. In the same way when bar magnet was moving, when bar magnet was there. So, from the second experiment, he has found the same phenomena, only either by replacing the bar magnet with the coil or coil with the bar magnet. Same type of observation he has found. It means galvanometer shows the same type of phenomena. It means when they are coming close, then the deflection in one direction, and when they are moving away, then the deflection in the opposite direction. Now see the experiment number 3. Now see in the experiment number 3. In experiment number 3, he took 2 coils. Let this be your one coil, and in this coil a galvanometer is connected, and in the another coil a battery is connected with the switch S. Now, what he has observed is the EMF of the cell. Right now when switch S is open, it means this circuit was disconnected. There was no current in the circuit. So galvanometer deflection was 0. It means galvanometer was not showing any deflection. It means there is no current in the branch. Now, what he has observed, as soon as the switch has closed, when the switch has closed, immediately at the same moment, galvanometer shows deflection. But after a fraction of a second, the deflection becomes 0. It means then there is no deflection at all. But again when the switch reopened, then again he observed there is deflection in the galvanometer, but it is in the opposite direction. So from this experiment, he has repeated so many times like this. So he observed that during closing and opening the switches, at that moment only galvanometer shows deflection. So it means he has concluded that there is no need of relative motion as we did in the experiment number 1 and 2. Even that in that case also galvanometer shows deflection. So he has concluded that there must be certain physical quantity which is varying either due to relative motion or due to closing and opening the switches. So see the conclusion from this experiment. From experiment 3, he observed that when switch S was open, there was no deflection. There was no deflection in galvanometer. No deflection in galvanometer. It means there is no current in the another coil. There is no current in the coil. But as soon as switch is closed, at the same moment galvanometer shows deflection. Galvanometer shows deflection, and that deflection persists for a fraction of a second. That deflection persists for fraction of second. So it means as soon as switch is closed, at that moment only deflection was there. Now he reopened the switch. At that moment also, he found deflection in galvanometer. But in opposite direction. So this is the observation from the experiment 3. It means during the closing and opening the switch. It means when we are closing and reopening the switch, only at that moment galvanometer shows deflection, and in both side or both time deflection was in opposite direction. So this is the conclusion from the experiment number 3. So from these 3 experiments, or we can write from above 3 experiments, he has concluded there must be a certain physical quantity, or there must be a certain physical quantity which vary or which changes. There must be a certain physical quantity which changes either due to relative motion between magnet and coil with galvanometer, either due to relative motion between magnet and coil, or during closing and opening the switch. During closing and opening switch S, there must be a certain physical quantity which changes either due to relative motion between magnet and coil or during closing and opening switches. Because of that, Because of that, a current develops in another coil. In another coil. So later he has introduced that physical quantity as magnetic flux. Later he has introduced that physical quantity as magnetic flux phi. So finally he said that there must be a certain flux, a certain physical quantity that is called flux. That flux is changing either due to relative motion between the coils or during closing and opening the switches. Because of that, the current is induced in the another coil, and that current is called your induced current. And current has induced because of the some EMF developed or some potential difference developed. That potential difference or EMF is called induced EMF. So now first we will discuss the what is magnetic flux and how he has defined magnetic flux. Now see the magnetic flux, how it has been defined. See, according to Faraday's, the number of magnetic field lines or number of magnetic lines of forces passing through a given area is called magnetic flux. So the number of magnetic lines of forces passing through a given area is defined as magnetic flux. The number of magnetic lines of forces passing through a given area is defined as magnetic flux. Since number of lines of forces, this is your simple virtual concept, or we can say it is your hypothetical lines, but the lines of forces properties are related to actual magnetic field. So as we know, the more lines, it means more magnetic field. According to that, so we can define the magnetic flux in terms of the magnetic field. So if ds is a small area in magnetic field B, then the flux, then magnetic flux d phi through that area is defined as d phi is your b ds cos theta, like this. Let this is your small area ds, and this have area vector here in this direction, and it is kept in a magnetic field B, and this B is making an angle theta with the area vector. So d phi written as b ds cos theta, and B is vector, ds area also vector, so that can be said B dot ds. This is the way of defining magnetic flux. Here theta is the angle between area vector and magnetic field. So this is the way by which we are defining magnetic flux. So we can write certain point related to magnetic flux. First point, magnetic flux is scalar physical quantity, with SI unit is Weber or Tesla meter square. With SI unit is Tesla meter square or Weber. Second point, the dimension of flux can be given as phi we can determine by using the dimension of B and dimension of area vector. So dimension of B by dimension of area vector, your L square. So dimension of B can be written as dimension of force by IL into L square. So dimension of F is MLT minus 2 by AL into L square. So finally, dimension of flux we can determine directly from here. L and L cancel. M L square T minus 2 A minus 1. M L square T minus 2 A minus 1. This is the dimension of flux. Now see the another point related to the magnetic flux. Now third point, magnetic flux through a closed surface is always zero. It means suppose this is any closed surface and this surface is kept under the magnetic field lines. When this surface kept under the magnetic field lines, so when we are talking about the total flux, the total flux can be written as incoming flux plus outgoing flux. Incoming flux means the lines which enter into the surface. Outgoing means lines which going out from the surface. See here, if I am talking about this part of the surface, in this part of the surface lines of forces are going inside. So magnetic field direction this, area vector direction this. So here in all these points, magnetic field and area vector makes an angle between pi by 2 to pi. It means angle between this here 90 and 180. So flux through this, according to flux relation, d phi is your B ds cos theta. So from this part you will get a negative flux, and from this part we will get a positive flux. So that part can be said as a phi incoming, and this part of area can be said as a flux outgoing. So flux incoming is equal to your minus of flux outgoing. So total flux will be here 0. So magnetic flux through a closed surface is always 0. Now see the another point. See the fourth point. If a magnet is placed inside a closed surface, then the flux through that surface, is also 0. Flux through that surface is also 0. See the meaning of that. Let this is any magnet. It has north and south pole, and it is kept under a closed surface like this. So what, as we know, north pole strength normally taken as positive, south pole strength taken as your negative. So we can say, as we know, from the north pole lines of forces your leaving and south pole your enter like this. So we can say here the number of lines of forces your leaving to that surface, same number of lines of forces are incoming to that surface. So through a closed surface, B dot ds is always 0. This is also called Gauss law for magnetism. Gauss law for magnetism. This is also called Gauss law for magnetism. Now, see the next point. If an area or surface kept in uniform magnetic field, then the flux through that surface, is given as the flux is equal to your magnetic field into projected area. This is the very important relation, and this relation is valid only when the field is your uniform. Just like one example we can say, let this is the magnetic lines of forces, and in the path of lines of forces let one cone is kept, and this cone have radius r and height h. Now question is that to find the flux through that cone. So flux through that cone, first of all, magnetic field, you see lines of forces are parallel and equidistant. So let field is here B, uniform field. So if uniform field is there, so we can apply this relation to magnetic field into projected area. So now magnetic field here B and projected area. How to get projected area? Suppose if it is a screen here, if the screen kept here like this, so which type of shape we will get on screen? See, if light beam is thrown from this side, so we can get a just like a shadow, triangular shadow, and the base of that triangle will be your 2r, while height of that triangle will be h. So that triangle like this, if I am making in this plane, so this type of shape we will get as a projected area. This is your 2r, this is the h, this is the projected area. So flux through that cone is written as B into area of that, half base into height, that will be r into h, to b r into h. This is the flux associated with the cone. Similarly, suppose we are having another example. Let a sphere is kept in the field. A sphere is kept in uniform magnetic field. Then see the which type of or how the flux we can calculate. Let this be your sphere of radius r. A sphere of radius r, and this is kept in uniform field like this, and the field is B. Here again, field is a uniform sphere. So what is the projected area of the sphere? The projected area of the sphere will be a circle. So then flux will be your B into pi r square. This is the flux associated with the sphere. Similarly, let we are having a cylinder in place of a sphere. See, let a cylinder is kept in uniform field like this. Cylinder of height h and radius r. If this type of cylinder kept in uniform field B like this, then see the flux. Again, if this is your cylinder, if I am looking the projected area, the projected area will be a rectangle of one side your h and another side of 2r. So this is the projected area. This is h and this is 2r. This is the projected area. So total flux will be here magnetic field B into area. So B into area will be your 2RH. Likewise, so in this manner we can calculate the flux associated with the different shape or different bodies, provided the field should be uniform. So for uniform magnetic field, flux calculation we can do by using this relation. Flux is equal to your magnetic field into projected area. Now see some different example in which let magnetic field is not uniform. See. Now see another example. In this diagram, a current carrying long conductor is given having current I, and in the plane of this, suppose a rectangular loop is given and the dimension of the loop is like this. To find the magnetic flux associated with the loop, we can write a rectangular loop loop is kept under the magnetic field produced by long current carrying conductor as shown in diagram. Find the magnetic flux associated with the loop. This is the question here. This is a loop which kept under the field of current carrying conductor. So you have to find the flux. Solution. See. As we found here, if we are moving from one edge to the other edge in this loop, the different part of the distance are at different distance from the conductor. So magnetic field is variable. So as we are moving from this edge to this edge, magnetic field value gradually decreases. So flux is not constant, or our loop is not placed in a uniform field. So what we will do, we can take a small element or a small rectangular like this, which is at distance r from a current carrying conductor, and d are the width of that rectangle, and b is this dimension. So this is the area. We can say dr is too small. So we will find magnetic flux through this strip first. The magnetic flux through this strip written as d phi is equal to b is the magnetic field into area of that strip, your b into dr. This is the flux through that area. Now magnetic field at this point, due to long conductor, which is your mu naught by 4 pi 2I by r into b dr. This is the flux d phi. Now simplify this one, mu naught IB by 2 pi dr by r, and we will integrate. Our r value means our loop is from here to here. So value of r is vary from d to d plus a. So limit of integration will be your d to d plus a. So then the flux will be mu naught IB by 2 pi ln d plus a by d. This is the flux due to current carrying conductor through this loop. Now see another example. A long cylindrical conductor of radius r having current I which is distributed uniformly uniformly across its cross section. A long cylindrical conductor of radius r having current I which is distributed uniformly across its cross section. An hypothetical surface has been made inside a loop inside a conductor as shown in diagram. As shown in diagram, find the magnetic flux associated through that surface. This is the question here. Question is that this is your long cylindrical conductor in which current is your I. Inside the cylindrical conductor, this is your hypothetical loop has been made. Hypothetical loop or hypothetical surface has been made, and through that surface we have to find flux. So first of all, long conductor, so magnetic field inside a long cylindrical conductor is given as magnetic field inside a long cylindrical conductor. Long cylindrical conductor is given as magnetic field inside a long cylindrical conductor is given as by using Gauss law. B dot dl or Ampere's law here, mu naught I enclosed. So B inside 2 pi small r mu naught I enclosed will be your I by pi r square into pi r square. So from here B inside can be written as mu naught by 2 pi r, pi and pi this cancel. So mu naught by 2 pi, then I by r square into, then I r by r square. This is the magnetic field inside the cylindrical conductor. Now, in this region we have to find the flux. As we have found here, magnetic field vary from the axis as the distance changes, and that distance is your small r. So again here we will take a strip of thickness dr and we will find flux through that strip. Just substituting the value of B here. So d phi written as magnetic field. The magnetic field already we have calculated. mu naught by 2 pi I r by r square, and then area. This is your length L, dr is the thickness, L into dr. Then we will integrate the mu naught I by IL by 2 pi r square r dr, and we will integrate limit from r0 to capital R. So finally flux will be your, this is your r square by 2. So here mu naught by 4 pi, and that r square cancel, I into L. This is the flux through the long cylindrical conductor within the your sphere, within the surface of or within the conductor. Now see another example. It is given magnetic field in space is given as B is equal to 3I cap plus 4J minus 2K cap Tesla. Find the flux associated with a rectangular loop of area 2 meter square kept along xy plane, like this. So we have to calculate the flux through a rectangular loop of area 2 meter square, and this is placed along xy plane. The xy plane, if we are looking the x, y, z direction, our xy plane is the bold plane. So area vector will be along z axis. So we can say area vector we can make like this. S cross is your S vector bar, 2 is the magnitude, and direction your either plus k or minus k, any direction you can take, because we want only flux associated. So total flux modulus of B dot S. So just do the dot product of this. B value given here 3I plus 4J minus 2K cap, and dot product your S plus minus 2K cap. When we are doing the modulus of that, K and K will be here 4. So we can say 4 Weber is the flux through the given area. This is the flux by this field. Now see another example. The magnetic flux. First see the magnetic field in space is given as B is equal to minus B naught x K cap. To find the flux associated with an hypothetical loop ABCDA, with an hypothetical loop ABCDA its dimensions are shown in the diagram. Shown in the diagram. Now see here. According to the question here, magnetic field directed along minus K cap. Minus K cap means inward as shown here in the diagram. But that magnetic field is not constant because it changes as X value changes. It is variable magnetic field. As X you are changing, magnetic field changes. So again, we will use the integration method. So what we will do, we will take a strip on this hypothetical loop. This is the strip at distance x from the origin, and let width of the strip here dx, and this is the dimension or length of the strip as b. So see the flux. Flux we have to calculate b. B value over there is your b naught x, and area of that strip, this is your dx into height your b into dx. This is the flux through that small part. That value we can say rather phi d phi. So d phi finally written as b naught b x dx. Now integrate b naught b x dx, limit of x from a to 2a, a to 2a, and simplify then b naught b by 2 x square means 4a square minus a square. So finally we will have 3 by 2 b naught b into a square. This is the flux associated with the hypothetical loop A, B, C, D, A. In this manner we are calculating magnetic flux for different cases.